In this video, we will look at transmit diversity. Previously, we have studied receiver diversity, where we said we have multiple antennas at the receiver and we are receiving the same signal at the receiver to get the benefit from diversity. And then we studied different schemes like selection combining, like co-phasing or equal gain combining, and then optimal combining, that is maximal ratio combining. So now we need to look at, if we do not have receiver diversity, so we need to do something to the signal before sending it from the transmitter. So that means when you have multiple antennas at the transmitter and the receiver, you only have single antenna, but still you want to gain benefit from the diversity. So that kind of diversity is known as transmit diversity. So that means you are doing some diversity pre-processing at the transmitter before the signals leave the transmitter side. So now you have uncorrelated channels, so you need to split the power. So you have equal power ES, you divide it across the channels. So then instead of the signal ST, you will not transmit ST directly from the transmitter, but you need to transmit the signal H1 conjugate divided by root 2 ST and H2 conjugate divided by root 2 ST. So we divided by root 2 because the total power we have is ES, and then we multiplied with the conjugate of H1 and H2. And if we send the signal in this form, then only we can take the benefit of co-phasing at the receiver side. And we have studied that in case of co-phasing, if we estimate the channel accurately, then we can do something to gain the benefit. But before that, to send the signal in the form H1 conjugate divided by root 2 times ST, what we first need to do is we first need to estimate H1 and H2 at the receiver. So we have channel corresponding to this branch as H1, and then we have here H2. So this is known as the channel state information. We need to estimate this channel state information at the receiver. And when this channel state information is available at the receiver, we represent it by CSIR, that means channel state information at receiver. And once this is estimated, we need to send a feedback signal to the transmitter so that the transmitter knows the channel state information. And now the CSI is available at the transmitter end, and we represent it by CSIT. So now the transmitter has the CSI channel state information available. So it can send the signal in an appropriate form so that we get the diversity benefit at the receiver. So that means once you have estimated the channel, you can apply optimal combining or you can apply co-phasing, just like we have discussed in the receiver diversity. And same is also valid for the transmit diversity, provided that we have a feedback coming from the receiver about the channel state information. So here we have two cases. So first thing that we need to do is we first need to estimate the CSI. So once the CSI is estimated, we need to send a feedback to the transmitter, and then the transmitter will send the signal towards the receiver. So we have two different cases here. Once the time is, this is the time required to first estimate, then send feedback, and then for the transmission. So this is the time required. So if this time is less than the coherence time, then we do not have any problem. So just recall what we discussed about coherence time. So coherence time is a time over which the channel is correlated to itself. For example, if let's say this is the coherence time Tc, and we have a symbol with duration Ts. If the symbol duration is less than the coherence time, then these 2 points, they are correlated to itself. And if this, let's say this is less than the symbol duration, if this symbol duration is greater than the coherence time, then in that case, these 2 points, they are not correlated to each other. So when this time is greater than, the coherence time, let's say this is the coherence time. So what you have estimated in the coherence time TC, then you send a feedback, but your transmission is not complete. So when the receiver will detect the signal, the CSI information, it has been outdated at that time. So that means when this time is greater than coherence time, you have a problem of outdated CSI. So this transmit diversity, you can only apply when this measured time is less than the coherence time. Otherwise, you have a problem. You have outdated CSI and you cannot detect the signals because the CSI has been expired and you have a new channel. So now what we can do if we do not have CSIT? So this question has been answered by the Alamouti scheme. So Alamouti scheme says that doesn't matter if you have CSI available at the transmitter. So you do not need to have CSI at the transmitter to gain the benefit of diversity. And how this is done? This is done by sending two different signals S1T and S2T from the transmitter. And earlier, if we recall, in receiver diversity, we have said that if we just directly combine these two signals X1T and X2T, we do not gain any benefit in terms of diversity. And this we have seen earlier. But now, and moreover, if we just treat this as the received signal, let's say this R1, and if R1 is equal to, this is the channel H1 and we have a channel H2. So R1 is H1 X1 of T, and this is H2 X2 of T, plus then we have noise. Okay. So now this is the received signal when we transmit two different signals from the transmitter. So if we send these two signals at the same frequency, they will interfere with each other. And when they will completely interfere with each other, in that case, we will have channel to interference approximately equal to 0. So we will not gain any benefit when we just directly send the two signals. So Alamouti said, instead of directly send the two signals, there is a way by which we can achieve diversity. So let's see that. So what he said, from antenna 1 at time 1, you send a symbol S1 or signal S1. Then at time n is equal to 2, from antenna 1, you send the second signal S2. Similarly, from antenna 2 at time 1, you send minus S2 conjugate. And then at n is equal to 2, you send S1 conjugate. So these are two different times. Or you can say this is the symbol periods. So we have two different symbol periods. So at two different times, we are sending two different signals from antenna 1 and antenna 2. So then we can write the received signal equation at the receiver. So we first have R1. So what we have sent at time n is equal to 1. We have sent S1 from here, and we have sent minus S2 conjugate from here. And then we have channel H1 and we have channel H2 here. So we can easily write the received signal equation. We have H1 times S1, and then we have minus S2 conjugate times H2, and then we have noise. So this is what is written here. So now at n is equal to 2, antenna 1 is sending S2 and antenna 2 is sending S1 conjugate. So again, we can write R2. R2 will be equal to H1 S2 plus H2 S1 conjugate plus N2 of T. So at two different times, we have two different receive equations, and we have two unknowns, S1 and S2. So we have two equations, two unknowns. We can easily solve for S1 and S2. But what is very important about this Alamouti scheme, how this is providing us the diversity gain. So now let us look at that form. So Alamouti said, you write your received signal in this particular form. So you write as H1 conjugate R1 plus H2 R2 conjugate. And if you try to solve this, you get this particular form of equation. And in this equation, you can see that it depends on the symbol S1. So that means you can easily detect S1 from here. There is no interference from the S2. And then you have some H1 conjugate N1 and H2 conjugate N1. This is basically the noise. They both are the noise terms, and the noise will get expanded. Rest all will remain the same. And in the signal part, if you look at, you have mod H1 square plus mod H2 square. So this is what we are having the diversity gain here. Because if one of the channel fails or one of the channel is in fade, still you can recover the signal S1 from the other channel. Isn't this what we discussed about diversity gain? Even in diversity gain, we discussed the same thing. What was diversity gain? So diversity gain was, we have multiple channels, H1, we have H2, H3, and if any of the channel is in fade, still you can recover the signal from the rest of the channels. So basically here you are getting a two branch diversity. Similarly, you can write another equation to detect symbol S2 conjugate. So if you have S2 conjugate, you can directly detect for you simply have S2. So again, you have the same equation. So this is again, we have two branch diversity here, and you can detect S2 from this equation, and you have noise corresponding here. We can represent this matrix in a form like you have S is equal to antenna 1, you have antenna 2, then we have time n is equal to 1 and time n is equal to 2. So from antenna 1 at time 1, you are sending S1 and S2, and from antenna 2, you are sending this one minus S2 conjugate and S1 conjugate. And this matrix S has a very special form, and that special form is that if you compute S as Hermitian, so you will get mod S1 square plus mod S2 square times the identity matrix 1 0 0 1. So that means this S is basically orthogonal. So again, if we try to write this received signal equation into the vector form, what we can write? So here we want to detect S1 and S2 conjugate. So let us write here. We want to detect S1 and S2 conjugate. And from here we have noise N1 and N2. And we want to write the channel here. So R1 is basically H1 S1. So we have H1 minus H2 S2 conjugate. So here we will have minus H2. And this is R1. So you have first equation R1. So now let us write for R2. So we have S2 conjugate here, and here we have S2. So we have basically H1 S2 plus H2 S1 conjugate. So basically we will take conjugate of this one and we will arrive to this S2 conjugate. So simply we can write H2 conjugate, and here we will have H1 conjugate, and here we have R2. Okay, so this is the channel represented in a matrix form. So again, if you try to compute this H Hermitian, so what you will get is you can represent it in the form H1 mod square plus H2 mod square multiplied by the identity matrix. So that means the orthogonality has been built into the transmitter before sending these two signals from the transmitter side. And when this is orthogonal, so H is basically orthogonal, and we know when H is orthogonal, we can easily detect these two symbols S1 and S2 conjugate by directly multiplying H Hermitian with R1. So this should be conjugate R1 and R2 conjugate. So if you have done this, at first time slot, you can easily detect S1, and then at the second time instant, you can easily detect S2 conjugate, and there is no interference coming from the other symbol. So this is why, because of this Alamouti scheme, we are sending two different signals. Still, we are gaining the diversity gain here, because if one of the channel is in fade, we can recover the signal from the other channel. Orthogonality has been built into the transmitter so that we get a robust detection and we do not require any interference cancellation, because this H is orthogonal, and when this H is orthogonal, you can easily detect S1 and S2 conjugate by directly multiplying H Hermitian with the receiver vector at the receiver. So now, if we try to compute the SNR in case of Alamouti scheme, so this equation is basically the general form of the signal that is received at the receiver, from where you can detect S1. And again, if you have to detect S2, then again you have S2 conjugate. This is again having the same form. So from here, so you can say that this is the general form to detect symbol. Okay, and now we want to compute SNR from this equation. So you have noise power, and then corresponding to the signal component, you have this term. So now let us try to write SNR. SNR is mod H1 square plus mod H2 square. Then you have to take again square here, and then you have ES by 2. And why by 2? Because we are sending two signals and has a power of ES. So we'll divide the power among the symbols. So we have ES by 2. So this is from the signal side, and from the noise side, we have mod H1 square times N1 plus mod H2 square times N2. So this N1 and N2 are basically sigma N square. So you can take this out, sigma N square. So you have sigma N square here, and you can write it in this form. So this one term will get cancelled with the square, and what you are left with is basically this part. Mod H1 square plus mod H2 square divided by 2 times ES by sigma N square. And from this expression also, you can see that this ES by sigma N square, this can be viewed as the SNR of single antenna. And this has the diversity gain coming because of the transmit diversity. So you have H mod H1 square and mod H2 square. Any of the channel is in fade, you can detect the signal from the other one. But here you have to know that we do not have array gain. So array gain was basically, if you instead from here, if you had like twice ES by sigma N square, then you can say that you have a array gain. But in this case, you do not have an array gain. So again, a very good understanding to understand this, why there is no array gain in this transmit diversity and why we have an array gain in the receiver diversity is as follows. So let's say you have a transmitter. So in case of transmit diversity, you have multiple antennas at the transmitter. And let's say you have one antenna at the receiver. So you have a total power budget of ES. So you divide the signal by ES by 2 and ES by 2. So this was the total signal that was transmitted. Sorry, ES was the total power that was transmitted from the transmitter. And at the receiver side, you have one antenna. So it will only get ES here at the receiver. So this was for transmit diversity. But however, on the other hand, when you have receiver diversity, so you have one transmitter antenna and you have two different receiving antennas at the receiver. So you are sending the signal with total power budget ES. And at the receiver side, this ES is captured by the first antenna, as well as this ES is captured by the second antenna. So that means two signals are received, which has a total power of ES. So you can have twice ES at the receiver. So this is why you are having array gain in case of receiver diversity. Whereas in case of transmit diversity, you do not have array gain. So the difference between this receiver diversity schemes and the transmit diversity schemes is that receiver diversity, you have diversity gain and you also have array gain. Whereas in case of transmit diversity scheme, you have diversity gain, but you do not have array gain. And this Alamouti scheme is also known as the space-time coding. So you are sending a signal. You are basically utilizing both the space diversity and the time diversity to send the signal and to gain the benefit of the diversity. And in the end, you get signals that are interference free. So there is no interference cancellation processing required at the transmitter or at the receiver, because orthogonality has been built into the transmitter so that signal can be received interference free at the receiver.